So now we're going to be doing problems 14, 15, and 16, which all build on each other. So the first step is that the switch has been in position 1 for a long time and then moves to position 2. So at first we're going to determine V naught, which is the position or the voltage that the capacitor is at before the switch moves. So we'll redraw the circuit right before the switch moves. So this section is gone. And we'll replace that with a wire right across here. And then the capacitor, because it's a steady state for a long time, is replaced with an open. That's VC. So now you might notice that the 2 ohm resistor is completely useless. It doesn't connect to anything. That makes our circuit analysis pretty easy, right? The 7 kiloohm also does not have any current flow through it because it has an open right next to it. So that means that VC will be equal to the voltage right over here. And then the bottom connects to the bottom of the 10 ohm as well. So VC is equal to the voltage of the 10 ohm. Current flows in this direction. So now we can just use the current divider rule. 40 over, this is 10. Okay, and that equals 25 volts. And this is just simple VDR. Next step, redraw the circuit in position 2. Determine the equivalent resistance as seen by the capacitor. Also determine the time constant and the final voltage across the capacitor. All right, so we're going to go back to the original circuit. And now we'll say, okay, so if the switch was in position 2, like that, what would the circuit look like? So effectively, the circuit would look like this with the 40 here. And if you notice, it doesn't actually connect to the other spot, right? Because this part directly connects to the 2 kiloohm, and then that directly connects to the capacitor. So we can actually get rid of this whole section, and we're just left with this section here. So I'll make that a little neater for you guys. So we have the 2 kiloohm, and then the 7K, and then the capacitor. VC, 7K. All right, so now the next step is to find the equivalent resistance, right? So usually the best way to do that is to remove the point of reference, which in this case is the capacitor. And we're going to replace that with an open. We're going to say REQ is going to be here. And then we will find the Thevenin resistance, which in this case is pretty easy. The 7 and the 2 are in series, so it's just 9 kiloohms. The next step is to find tau. So that is RC, R being the Thevenin resistance or the equivalent resistance, and C being the value of the capacitor. So the capacitor was 5 microfarads, and the Thevenin resistance was 9 kiloohms. So we're going to get 45 milliseconds. And lastly, final voltage. So, I mean, if you look at it, we have our capacitor here. Capacitor's right here. And there's no other source. So, logically, it will eventually decay down to 0 because there's no battery to keep it charged. So now all that's left is to draw the curve that it's connected to. So develop a transient response equation, and then we have to plot it. So we'll use the general equation. I recommend always using the general equation. The other ones can be convenient, but you can get tripped up and miss a term if you don't know how to use them properly. So generally, it's always best to go with the general equation. So all you're going to do is plug in the values that you already found. Vt is equal to 0 plus 25 minus 0 e to the negative t over 45 milliseconds. And then we'll simplify that by getting rid of the zeros that we don't need. So just 25 e to the negative t, 45 milliseconds. And that's in volts. All right. Now, when we do the curve, we need to make sure we have 2 points labeled. We have to have the final voltage, which is 0, and the initial voltage, which is going to be 25 on the voltage side. Now this side, we're going to put this in milliseconds because that's what our tau is in. And we have to label the endpoint, which is always going to be 5 tau. That's 5 times 45. That's 225 milliseconds. All right, so now we're going to start, because this is a decay curve, and we know it's a decay curve because it goes from 25 to 0, and it's always going to be exponential. So that means you start from a high point here, and you slope down. Now this software makes it difficult to produce that curve, but you're going to end up with something like that. Maybe a little smoother around this side right here on the left, but something like that. Just make sure it's not linear. Your teacher probably would only mark you off if it was linear or some other crazy shape. If it even kind of looks like this, you're probably going to get full credit. And that's problem 14, 15, 16.